Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science, and in this lecture series we are having the subject called theory of computation. And as far as the previous episode is concerned, we have seen that the conversions of regular expression to NFA with epsilon transitions, and then we have just seen that is how the regular expressions are computed from the given deterministic finite automata. Here the condition is, if you are interested in evaluating the or computing the regular expression from the deterministic finite automata, the deterministic finite automata must be the minimal state deterministic finite automata, and it should be unique, so that the computation of regular expressions will be much easier and it could be done without any difficulties or without any ambiguities also. So, that is what we are given a deterministic finite automata, and then we have to find out there is equivalent regular expression. As far as the computation of regular expression from the deterministic finite automata is concerned, we need to define a recursive definition, and the recursive definition we will be giving a notation that is Rijk, and what it denotes is from the starting state there is I, and to the final state there is j, with the help of the intermediate states numbered not more than k. So, I and j are available in the suffix and k is going to be available in the superfix, and this notation will describe in turn that is the entire regular expressions denoted by the given deterministic finite automata. So, that notation also we had seen as far as the previous lecture is concerned. So, in this lecture we are going to have the complete recursive definition of the notation that is Rijk, and once this Rijk is defined, then it is possible to convert any given regular expression or any given deterministic finite automata into its equivalent regular expression, or the computation of regular expressions can be done from the given deterministic finite automata. Let us see, that is the initial stage. So, since it is going to be a recursive formulation, we need to find out what is going to be the basis. Basis is the automata with no intermediate state. So, we can have any automata, but the condition there is any string which we are generating out of that automata should not include any intermediate state. So, that is what we are fixing the k value as 0, but whereas I and j can be anything. So, given an automata with 10 number of states, this I can be 1 and j can be 10, or I can be 5 and j can be 7, or even I can be 7 and j can be 1 also, provided there is a loop which is forming that. But the condition there is, if the k is equal to 0, then immediately we can say that there is no intermediate state. Suppose if we do not have a transition from I to j with some label I, some k or a, then it means that the string available or the pattern described by that particular transition is going to be empty. That is what, if there is no symbol as transition from I to j, then actually the notation is R I to j with the superfix 0, the language is going to be pi, because we do not have any label available on that particular automata. So, generally we will be having something like empty language. So, empty language means a language with no number of strings or no string at all. So, how do you describe the language with no string at all? You go for an automata with a state marked as starting state, and there will be a state with the final state, there is final label or which is double circle, and ensure that there is no transition from the starting state to the final state. So, if there is no transition from the starting state to the final state, then we can say that the language of that automata is going to be empty. So, here the process is completely reversed. Given automata with no transition from the start to final state, how do you find out the regular expression described by that particular automata? The regular expression which is describing the empty language is designated as pi. So, if you find that no transition from I to j with any label, then immediately you identify the regular expression as pi. So, that is going to be the basis for the regular expression formation from the deterministic finite automata. And one more case is, if there is one label, suppose we find that I is the state, starting state, and j is the state where we will be terminating. Once again, there is 0 for k, it means no intermediate label or intermediate state. In that case, if there is a direct edge available or direct transition available from I to j, there should be a label available for that I to j. And suppose if the label is going to be a symbol that is a, then the regular expression denoted by the pattern R I j with 0 as a superfix is going to be a. Sometimes there may be more number of labels available in the transition from I to j. We may have something like starting from 1 to there is 2. If it is a comma b comma c, then we need to include a as a regular expression, b as a regular expression, and c as a regular expression. But the very important thing is, it cannot be a, b, c, but it should be either a or b or c. So, that is what we mean by the second that is point in this slide. So, if there are symbols a1 comma a2 comma a3 up to ak as labels in the arc from I to j, then still the pattern is described by the same notation R I j with the superfix 0, but what is going to be regular expression is, it is a1 or a2 or a3 or a4 etc. up to ak. The OR operation is very important, because the language described by such an automata, I mean that is the automata with I as a starting state, j as the final state, no intermediate transitions. In that case, the language recognized by that automata is the set of strings, either it is a1 or a2 or a3 anything up to that is ak. So, we have seen two cases. One is there is a path available from I to j, but no intermediate path, no intermediate vertex. Another one is no path at all from I to j. If there is no path at all from I to j, then the language is empty. If there is a path from I to j without no intermediate state, then in that case we will be calling it as exactly the label available on those number of transitions, that is from I to j. It can be a single label or it can be any number of labels. Single label means that is the only regular expression. If you are having more number of labels, every label will be considered individually as a regular expression. Actually, these are the basic cases. So, now the question is how we are going to form the regular expression in a recursive manner, that is with k as any value greater than 0. As long as k is 0, then the formulation is basic. With the k is more than 1, more than that is 0, so in that case we must recursively explore this particular regular expression in order to find out what is the exact regular expression described by that particular automata. First, we should know the recursive definition of that. Here is the recursive definition. Before looking at the definition for I or ijk, we shall see how the automata looks like. We have a start state, it is I, and we have the final state, that is j. Now, we are going to find out what is the regular expression described by the automata with the start state I and j as the final state. The very important thing is, it is going to be recursive for the first time when we are introducing k there. It means the regular expression is divided into parts, and each subpart is going to be a regular expression formed with at most k minus 1 as the intermediate state. Actually, we want to form the regular expression described by the automata with I and j as the start and final states, and no intermediate state k labeled more than k. So, that regular expression is described in terms of the automata with no intermediate state labeled, that is even that is k. That means k minus 1 can be the maximum numbered intermediate state. So, here we have splitted it into, that is two parts. The first one is you move from I to j, but no question of taking any state as the intermediate state whose number is either k or more than k. If it is a condition, then the only path is from I to j, and that can go through any number of intermediate states. That is what we are having the dotted lines here. It can go to any number of intermediate states, but not k or more. So, how do you describe that regular expression? It is going to be I to j with at most k minus 1 as the maximal numbered intermediate state. The pattern is described by r I j k minus 1. That is one component of a regular expression. The next component of a regular expression is we are introducing k as the intermediate state. If k is introduced as the intermediate state, we have three subcomponents inside the regular expression. One is what is the pattern described by the start state I to k, but k not as an intermediate state. It means you can't repeat k. In that case, the regular expression is what is the start state, that is I, and the final state is going to be k. Since k is for the first time introduced, there is no question of having any intermediate state either labeled k or more. So, the pattern is now described by r I to k with k minus 1 as the superfix. The next is you start from k and you go up to j, because j is going to be the final state. Once again we are starting from k but not repeating k. If you do not repeat k, then k minus 1 is going to be the maximally numbered intermediate state. So, the regular expression described by k to j is now denoted by r k to j with the superfix k minus 1. So, if I am combining I to k and k to j, I have a new regular expression, that is a concatenation of r I k k minus 1 and r k j k minus 1. So, now we must understand that k is an intermediate state, but once the state is made as the intermediate state, we can visit that k any number of times. That is what we are having the next, there is transition here. You start from k, you can come back to k through visiting there is any number of intermediate states, and all these states must be numbered less than or equal to k minus 1, because for the first time we have introduced k and no question of having any intermediate state numbered more than k or even k. So, the path, if you are taking this, the regular expression denoted by this path is going to be r k to k, because starting from k and we are ending with k, and the label available on the intermediate states, it is at the most k minus 1. So, now if you are looking at this particular path, it may be either taken or may not be taken, or any number of times we can take this path. So, what is the new regular expression which is formed out of this? So, either it is going to be the path from I to j directly without visiting k, or it is going to be the path from I to k, visit k as many times as we needed, and then k to j. So, now look at the definition for the regular expression, that is r I j k. This is the first part. We are having regular expression from I to j, but at most k minus 1 as the intermediate state, that is the path denoted by I to j directly. Otherwise, it is going to be the concatenation of three number of subcomponents from I to k with k minus 1 as the maximal numbered intermediate state, followed by k to k with maximal numbered state, that is k minus 1, but it should be under closure, because this path can be visited any number of times including 0 times. So, if you are moving from I to k and no question of repeating k to k and directly going from k to j, means we will be taking 0 times of r k to k k minus 1. So, we need to have a closure there, or it can even be any number of times also, but that is not going to be the end, and we will be going for the third component of regular expression, that is going to be r k to j and k minus 1. So, this is the regular expression recursive formulation of the regular expression and how it is formed from the deterministic finite automata. The thing is, you find out what is the starting state, what is the final state, and what is the maximal numbered intermediate state allowed in order to form the regular expression from the deterministic finite automata. Let us continue the lecture after a short break. Welcome back. See, before the break we have seen how the recursive definition is formed for the conversion of non-deterministic finite automata into its equivalent regular expression. In fact, the finite automata and regular expression both are the tools meant for the regular languages, but still it is required to find out the regular expression from the non-deterministic finite automata. The recursive definition is having lot of operators, plus if there is your union is there, then concatenation is there, and then closure is there. There is a need for doing the simplification of the regular expressions which are formed from the deterministic finite automata. So, we need to have a look at what are all the various algebraic identities and what are the simplifications available for the regular expressions. Let us see what are the simplifications which are possible as far as regular expressions are concerned. The first thing is, when you are having the R of two regular expressions which are same. So, it is going to be, if it is R plus R, or in simple words it is going to be A or A is going to be A only, and if it is A or B you can't go for simplification. The next one is, suppose if it is a regular expression R or another expression which is going to describe empty language, then the language of the regular expression is going to have at least the language of R. So, the new pattern is going to be R. And the next one is, when you are concatenating any regular expression with the epsilon, the regular expression resulting is going to be exactly R only. If it is R plus S, we can even write it as S plus R because it is going to be commutative, and R plus is equal to R followed by R star, that is it is going to be the positive closure either one time R or more the number of times of R. So, this is formed by one time R followed by 0 or more times of R. Then if you are having any number of times epsilon, it is equivalent to 1 epsilon, and if you have there is the concatenation of R with pi, then what do we have is going to be pi, because of if it is going to be the concatenation, you recognize a string from the first part of your regular expression followed by recognize a string from the second part of your regular expression. In the case of the second part, we will not find a label from start to final state. It means even after recognizing a string from R, we can't recognize anything from the second part. So, totally it is not possible to move from the final initial state of the automata to the final state. If we cannot move from the initial state of the automata to the final state, then the resulting regular expression is going to be pi only. And the next one is closure over closure, it is same as one closure. The next one is pi star, which is equal to epsilon. So, pi itself is a regular expression, but it is describing nothing or an empty language. But what will happen, suppose if it is going to be the closure of the empty language? When you are looking at the closure, definitely there is a string called epsilon available, that we can see by just constructing the equivalent NFA of the epsilon transition by using the Thompson construction. We will introduce a start state if it is a closure, and we will introduce a final state. The start to final is connected always by label epsilon irrespective of whatever the regular expression we are having. So, whether the regular expression is going to be pi or A or any complex regular expression, we will be introducing a transition from the start state to the final state labeled epsilon, and that will definitely recognize a string called epsilon, and it is not capable of recognizing anything more than that, because even if you take one time of that, there will not be any transition from start state of this pi to the final state of this pi. And one more is going to be R question mark, it will either select R or it will simply leave. It is very close to your plus. In the case of plus, it is 1 or more number of times, and as far as question mark is concerned, it is exactly 1 or 0 times of R. So, by seeing these primitives, it is possible, or we will find that it is very simple to convert the given finite automata into its equivalent regular expression. because we have a lot of there is expansion for the recursive definition, and we will find out lot of sub Rayleigh expressions generated, and every time if you are not simplifying the Rayleigh expression, finally we will find it very difficult to find out the or summarize the final Rayleigh expression which is described by the finite automata. That is what we are studying the similarities, and all these can be made use as far as the simplification of the Rayleigh expression is concerned. Let us see an example which is showing you how the Rayleigh expression is obtained from the deterministic finite automata. So, here we have a deterministic finite automata. The start state is 1 and the final state is 3, one more state, that is intermediate state, that is 2, and the transitions from 1 to 2 we have, there is 1, 2 to 3 is 1, and even if we have a back edge from 2 to 1 it is going and it is labeled 0, and you can find out that the automata is deterministic because no state is having there is more than one transition for the same symbol. And here in the 3 we have a self loop with labeled 0 comma 1. So, when you are in 3 we can come back to 3 any number of times irrespective of whatever the symbol we are having, it can be either 0 or 1. Now, the question is, how do you first of all describe the Rayleigh expression denoted by this Rayleigh expression? Find out what is the start state, what is the final state, and what are all the allowed intermediate states. To find out the Rayleigh expression denoted by the entire finite automata, we must allow every state be intermediate state. So, 1 should be the intermediate state, and 2 should be allowed to be the intermediate state, and even 3 should also be allowed to be the intermediate state. Then only we will be able to see the entire set of strings recognized by this automata, so that we will be able to come up with the actual Rayleigh expression for this automata. The expansion is R13 with 3 on the superfix. So, by the definition of that, first it is going to be 1 2 3 with the superfix 2, because we are recursively there is exploiting till we reach the basis case. A case is said to be basis if the superfix is going to be 0. So, till we get 0 we must expand this particular Rayleigh expression. It is 1 to 2 with the superfix 2, it is R. Now, we are considering even 3. How do we consider the Rayleigh expression that is going to be 3? So, that is going to be 1 to 3 with the 2 as the maximal numbered intermediate state, and you are going from 3 to 3 with the 2 as the intermediate state, but this can be repeated any number of times. So, it is going to be the closure, and finally, the left component is R 3 to 3, that is from 3 you go to 3, and once again it can be at most there is 2 number of intermediate states. Intermediate states can be either numbered 1 or it can be even 2. So, now we have there are 4 number of components available, R132, R132, then R332 and R332. In fact, only 2 are there is distinct, others are same. So, we need to compute all these expressions in order to find out the actual Rayleigh expression represented by this particular automata. The first one we are exploring is R132. Once again, by the recursive definition of that, R131 it is R, R122, that is actually the k value, it is I to k with the k minus 1 as superfix, here it is k to k with the k minus 1 as superfix, and here it is going to be k to j with the k minus 1 as the superfix. So, here it is 1 to 2 1 and 2 to 2 1 with the closure, then 2 to 3 with 1. So, now we are expanding this R131. So, we will be having all these basis cases now, R130, then R110, R110 and R130. Let us go back to the actual automata. The automata will tell you that is what is going to be the 1 2 with 0. As far as this particular expression is concerned, it is going to 130. In the case of 1 2 3 with no intermediate state. So, with no intermediate state means you find whether there is a transition from 1 to 3 or not. We have a transition from 1 to 3, but what is its label? It is 0. So, the Rayleigh expression denoted by R1 to 3 with 0 on superfix is exactly the label available on the path from 1 to 3, that is nothing but 0. So, that is why we are having 0 as far as R130 is concerned. The next one is what is going to happen for R110. 1 is the starting state, we are coming back to the same state because source and destination are same since R11 is to be evaluated. And what is the allowed intermediate state? there is no intermediate state allowed because the superfix is 0 here. So, now the question is, we do not find out any transition from 1 to 1 with the superfix, that is without any intermediate state. But can we say that the language is going to be empty? The language cannot be empty. Suppose if you are in a state that is I, and if you want to come back for I, but even then if you find that there is no transition from I to I, there is no point in saying that the language is going to be empty, because you are in I and you can stay back in I as long as, even if there is no transition or no string recognized. So, how do you declare or how do you define that language? The language is going to be a string containing only empty symbol, that is an empty string, because you are in I, you can stay back in I even without consuming any symbol. So, for any case, if the source and destination are going to be same, find out what is going to be the superfix, that is the maximum number, that is your intermediate state. If it is also 0, then you find out whether there is any, that is, loop available or not. We may have some loop, maybe in this automata itself we find that R33 with 0 is going to be either 0 or 1, because we have a transition from R3, so state number 3 back to the state number 3 with label 0, 1, but it is not always the case with other states. As far as state number 1 is concerned, we do not have a self loop, no transition from 1 to 1, but still we must write the Rayleigh expression denoted by R1 to 1 with 0 as the intermediate state is going to be epsilon, because we can stay back in the same state even without consuming anything. But if we make it as pi, then it means that we do not have any path from I to I, but that kind of situation will never arise, because you are in a state, you are interested in coming back to the same state, there is no point in saying that no transition available. We can stay back as long as we want, but without consuming any symbol. So, that is the reason why we are having, that is this R1 to 1 0, that is going to be epsilon, since we find that no transition from 1 to 1 with a label. But suppose if it is going to be R3 to 3, then in that case we find a label from 3 to 3 with the, we find a transition from 3 to 3 with label 0, 1. So, if the question is R33 with the superfix 0, then the output is going to be 0 or 1, because we can move from 3 to 3 with label 0 or with the input 0, or even we can move from 3 to 3 with the input that is going to be 1. But in the case of 1 to 1, the label must be epsilon. So, we have, that is 1 to 1 0 is epsilon, 1 to 1 0 the star is going to be epsilon, then 1 to 3 0 is already computed, that is also 0. So, epsilon any number of times you take the closure, still it is going to be epsilon. Concatenated with the epsilon will give you only epsilon. Epsilon concatenated with 0 will give you only once again 0, because 0 epsilon is going to be the concatenation, that is identity, and now we are having 0 or 0. So, 0 or 0 is going to be 0, it is because of A or A is going to be 0. So, A or A is going to be A only by the definition of the union operation. If you have, that is A, once again we have A, if you are taking the R of A and A, then the answer is going to be A only. So, finally we are having, that is the Rayleigh expression, that is 0. So, this is just the one part of the entire Rayleigh expression denoted by the particular that is deterministic finite automata. To find out the entire Rayleigh expression, we keep evaluating all the expressions which are evaluated as per, or which are expanded, or which are obtained by expanding the Rayleigh expression, that is R1 3 with 3 as a superfix. After computing all these, we just merge the Rayleigh expression as per the formula which we are obtaining and do the necessary simplification or do the maximum simplification possible, and finally we will come up with the Rayleigh expression, that is going to be the Rayleigh expression denoted by this particular deterministic finite automata. So, it may be that is simply application of the recursive definition and simplifying the Rayleigh expression to get this. As far as the question component of this particular part is concerned, we may be given any, that is deterministic finite automata, and you can find that what is going to be the start state, what is going to be the final state, and if you are interested in evaluating the entire Rayleigh expression denoted by the automata, then the final state must be made as the maximum numbered intermediate state. Sometimes he may be even that is asked to find out portion of that, maybe that is from 1 to that is 4 or the 3, with a small number as the maximal numbered intermediate state. In that case it is much easier, but if it is the maximum numbered state is going to be the final state of the automata, then the pattern is going to be the complete description of the entire regular expression. So, we have seen the construction of regular expression from the deterministic finite automata with the help of the recursive definition, and to find out the final regular expression it is required to have the simplification of the entire expressions, so that the expression whatever we have constructed is going to be unique, and that is for the deterministic finite automata recognizing the same language, whether it is DFA or it is going to regular expression, it is describing the same language whatever is described by the regular expression and deterministic finite automata. Here is one problem available with the Q1 is the start state and the Q3 is the final state. We are having Q2 as the intermediate state and some more transitions are all available. So, you can find out, suppose if you want to find out the entire regular expression, start from Q1, that is R Q1 Q3 with Q3 as the intermediate state. So, that will compute the entire set of regular expressions. So, that is about the question part, and with this I complete this lecture. Thank you all.